Okay, now in the second step of the exercise, so we are going to look into the heat transfer coefficient variation against the varying the flow conditions. So what I am going to do here is, so I take the laboratory handout and then I go into the second table where you can fill your data, and here you are again asked to maintain certain flows. So you can do that as the same way. So to get this 6 cubic meter per hour the air flow through the reactor, so you are supposed to set the 38% on the second rotometer that is defined by our previous calibration. So I increase the flow here to get 38% reading on my second rotometer, which is corresponding to 6 cubic meters per hour, and then I'm trying to calculate the heat transfer coefficient at varying flow conditions. But every time, don't forget, we have to maintain the same surface temperature in the pipe during this part of the exercise. So it is given here, and you must maintain 190 centigrade as the surface temperature. So now when I press number 3 here, I can see my surface temperature is only 40 centigrade. So I need to increase the surface temperature to the level which is given in the handout, that is 190. So what I do is I set the flow is settled now. So then I increase power to the electrical heater which is inside the pipe. So you can see that when I am increasing power, we get readings on the ampere meter as well as the increased voltage, and then we can see the temperature is rising. So I have to wait a little while to get stabilized at 190 centigrades, where the electrical power given out of the electrical given out by the pipes is equal or is well balanced with the heat taken away by the fluidization, the flow. And when I am at that condition, when I am at a stable at that condition, only I can take current and voltage readings to calculate the heat transfer coefficient, the formula, using the formula which is also given in the handout. But I would like to mention here, I mean, when you are taking these readings, this is very tricky, and so you have to have very good patience to maintain or reach the equilibrium points. And if you are in hurry, and if you are adjusting too fast this electrical setup, so you will never be able to get the stable conditions. And but even you may read the same or temperature. It's not controlled by the process itself. It can be controlled by the electrical the protection guard. And if you are at this condition, or if you are at this wrong condition, you will see these indicators going on and off, on and off. That means you are not at the equilibrium to take the heat release by the heater, and the heat absorbed by or taken away by the flow. So you always have to have the stable condition of the voltage and current readings if you are if you are correctly at the stable at the measurement point. That is very important when you are taking the measurement. Otherwise your readings will lead you to the wrong calculation. What I have pointed out is probably can be seen now. If I increase a little bit, so you see now the voltage and current readings came down rapidly and went out. That means the heater is controlled by the electrical protection system, it is not at the stable condition with the heat transfer. So you need to reduce the power and also maintain the same 190 centigrade temperature to keep the system under the stable conditions. So then only you can record your readings. So once you have done with that, and then you can reduce the flow to the second level. So before you reduce your the flow, you must reduce your power as well, because then otherwise it leads to overheating or increase the temperature of the heater. So by doing this very carefully, you can complete all these readings, and then you can plot the graph against the flow and the heat transfer coefficient, and there you will see some interesting information, and which we will see under the discussion on the results.